Okay, now we're recording. So who wants to tell me what recursion is?
Isn't it just a function that basically calls itself?
Yeah. So it's a function that calls itself. So what if I write a function like right here? Let's see, def func, and so can I do this? If I try to run it, let's see. Oh, I forgot to push up the boggle code. I'll do that later. Okay, what if I do something like this? Okay, so I can do that. Looks like it works. Am I not?
You're not calling it after you define it.
Oh, thank you. I was wondering why my computer wasn't blowing up.
Why don't you get yourself in an infinite loop?
So, who wants to tell me about what's happening here?
Are you returning the function itself?
Yeah,
Why
that
would-
might. I don't think that would actually matter. So it depends on what your function is doing, whether you return it or not. But
See now, yeah, this error makes more sense because it's about max recursion depth.
the other one was also
Is also the same.
the same error.
Ah. Okay.
But yeah, so what's happening here?
Not
There's
reaching an
no way
exit
for the
case.
function to end.
Yeah. So the function is never going to end, and the Python interpreter is basically saying, you probably don't know what you're doing, so I'm going to go ahead and stop you right now. So I think something like 1,000, it by default, you can actually change that configuration. But so what does this mean? The maximum recursion depth exceeded.
Isn't that like the call stack limit? How many processes or operations it can do before it exceeds the limit?
Yeah. So it's we'll talk about the call stack in a sec, but yeah. So this is the problem that you're going to have when you first start doing recursion is call stack, maximum call stack depth, whatever specific term, a stack overflow, right? So a stack is actually kind of a snapshot of your, it's like a snapshot of your execution context, basically. So I call a function, and then my function call gets put on the stack. So this is like the stack of things that my application needs to execute. But when I call the function again, it's just like, oh, I got to add something else on. So it can't really resolve the first case until it resolves everything else. And since that never ends, the initial case is never ever going to get resolved. So it's not the end of the world that you get this. You're going to get this error all the time, and it's fine. It's kind of like the iterative equivalent is doing an infinite while loop, except your computer will actually just blow up if you do an infinite while loop, right? Because there's no check. There's no check for while loops. So maybe that's one handy benefit to recursion. Okay, so recursion. So I have this recursive function, but it's returning another recursive function. Is this all there is to recursion? If I want to write a useful recursion function?
You should always have an exit condition.
Yeah. So as it is now, this function is really good at continuing to go, and it's really bad at stopping. So we need to give this function the ability to stop at some point. So that's typically called a base case. So when you're thinking about making a recursive function, maybe the first thing you want to think about is, when is this thing going to stop? Right? So I want to do a whole bunch of stuff. When is it going to stop? So I have a base case. So let's do something like well, actually, we'll do it if true. So this is actually never going to get called, which is fine. We'll look at an example in a second of actually doing this. But before we do that, let's try to. So recursive functions have two basic things you have to do. So if you want to write a recursive function, you have to have a base case, which stops it. You have to have a recursive case, which keeps it going, right? So you need to have a problem that you can break down into some repeatable algorithm that can be applied over and over and over again to the problem. You break it down into smaller and smaller pieces, and then once the problem is solved, and once you reach the end of wherever you're trying to get to, then you stop the recursion. So let's look at solving something iteratively. So if we want to count down, right, we can use Python, we can count down. So we just want to print from 10 to 1. So that's fairly easy to do. We can just do a for loop for we can use range, and then we can tell it, we can see the stop start. So we'll stop it. I think it's start stop. So we'll start at 10, we'll stop at 0, and we'll decrement by 1 every time. So if we run this, 1097, right? So that works. We're familiar with this. This is iterative. So we can count down from 10 to 0, or 1 in this case, iteratively. And that works fine. We can also do it recursively. So any problem that can be solved iteratively can also be solved recursively. So we can do something like, let's do def countdown. Let's countdown recursive. And let's just try doing this right here. So if num equals 0, return. I'm going to write this out, and then you guys can tell me about what's happening here. Let me just make sure that this actually runs. Okay. Okay, so this puts out the same input that we got from the iterative version. This may seem more confusing and less intuitive, which is fine. Recursion is one of those things that if you don't already get it, it's probably going to take you a little while to get, and that's fine. So
wait, where is it subtracting by 1?
I don't think that ran properly.
oh, dang it. What was I running? Countdown. Okay.
You didn't call it again.
Thank you very much. So we're going to do okay.
Yeah,
You aren't calling it, John.
Oh my God. Okay. Okay, so there we go. Thank you guys for helping me out. Sometimes, when you're doing this stuff live, it's easy to miss things. So I appreciate don't just let me get away with making an obvious mistake, please. Okay, so countdown recursive, it's calling this. So now that it's actually working, can anyone tell me either, how it's working in general or any specific aspect of what's happening?
So,
God. No, go ahead.
so each time it's called, you're going to evaluate, or it's going to print the num, and then you're going to subtract 1 from that number. And then at that point, you're going to evaluate. And if the num is 0, then we'll return, and then you'll start basically just pulling out of that call stack. But if it's not, then you're going to go through it again, which will then print the number, then subtract 1, and you're going to go through until num gets down to the point where it equals 0, and then you'll return.
Okay. So we can actually take a look at the call stack if you want to real quick. We'll talk more about that later, but for now, let's run the debugger. So I set my breakpoint here. So I want to run the whole function. Go into the debugger, run and debug. It's a Python file.
I think it's
Okay.
also, sorry to interrupt you. I think it's
Yeah.
really important to have a picture of what is going on so that you can picture the recursion. So think of a function as a window. And so whenever it calls itself, it creates a new window and it keeps on going. That's why you need if statements to tell it, hey, this is when you stop and this is when you do something else. So if you guys are struggling with this, I would write the functions as windows, and whenever it calls itself, there should be an arrow going in to a new window and what it's doing and why it's stopping. I know it's a long way of figuring out recursion, but that's how I solved it, and I get it now. Sorry to interrupt you.
Yeah, no, so that's a good point. And one of the reasons that we're going to look at the debugger is because it will help you do exactly that. And in another hour or so, we'll look at a tool that will help us visualize that. So for now, we can see that this function, so this is like the entry point for our application. And then the countdown recursive gets called. So now this gets put on the call stack, right? So we have now this function is on the call stack. It's going to run. So most like a non-recursive function, it'll get put on the call stack. It'll run till it completes. And then once it returns, it gets popped off the call stack. And you can go on to the next thing. But if it doesn't return, instead it calls something else, it's just going to keep adding on to the call stack. We can see the call stack here. You see how it's just building up. We just keep going down. So it's building up, building up, building up. You can keep going. You get a whole bunch of stuff on the call stack. But if we look at each, if we examine each call stack, you can see, we can look at our variables. Num should not be 3. Oh, it's because it's changing the. That's strange.
Why does it just skip over global num when it runs again? Because it just looks to me like it would just grab 10 from outside the function and just keep printing out 9, I guess.
Sorry, can you ask that question again?
Yeah, so the beginning of the function, it calls global num, which is 10.
Uh-huh.
Like it starts at 10.
Yeah.
So why, when it's called, when the function is called again, is it not just grabbing 10 again from outside?
Because
function?
I'm changing it on line 11. I'm changing this value So the first time it runs, I'm printing it out and it's 10 the first time, but then it's 9 now on line 11.
So when he's using global for that num, that means he's changing the num that's outside of the function. So he's not just continuously calling 10 into the function. When he calls like global num inside of that, that means that he's changing the num that was first created above
Right.
the function.
Okay.
So I'm doing it this way. This is actually not a good way to do it. You shouldn't be using globals if you can avoid it. And we'll look at a way that we can keep everything confined within the function. We're doing things recursively. But for now, I'm gonna have to hand it over to our guest. So I think Tom is gonna do the introduction. I'll stop sharing. You can just hang out for a sec while
Is Modi on the line? I don't think Modi's on.
okay, well, it's like 1 minute too, so I don't want to start getting into a new topic.
Yeah.
I mean, if Modi, I don't know if Modi is a guy or a girl, but
She's a girl.
okay. So if she's still coming, right?
Yeah.
Okay. I can share my screen. So we're kind of looking at this case of recursion basically as an alternative to iteration. And there actually are some languages that don't even have things like for loops. So you can't iterate. So you have to use recursion to iterate basically. So here in this recursive version of a countdown, we're basically, we are doing recursion, but this is kind of like the most marginal use case for recursion. But right now, the way we're doing it is we're using this global variable 10, and then we're changing that. So this is not a best practice, right? So how can we refactor this a little bit to get rid of the global variable and keep num confined to the local scope of the function?
You could pass num as a parameter and then call it with num -1
Okay.
within the function.
All right, so we do this. We'll get rid of this for now, this line. Get rid of that. You can get rid of that. We'll clean up the spacing a little bit. Okay, so now we're calling this, if we want to count down from 10, we call the function, it prints out 10, for example, checks if 10 is 0, it's not, otherwise it returns 9. So now num is 9, prints 9, it checks, is num 0? Nope, it returns 9 minus 1, so 8. So it just keeps going, so it does the same thing. 10, 9, 8, 7, 6, right? So this is basically how you can do that. You can also use default parameters for other things. So sometimes you might need to use a default parameter. So let's just say, instead of countdown recursive, let's do countdown from 10. We don't want to give it a parameter. Something like that. We could make this a default parameter. So this will start at 10, and then it should be the same. Oh yeah, change the name here. So the default will be countdown from 10. If you pass it a parameter, you could modify it that way. Okay, so sometimes default parameters is a useful way of keeping information within a function. All right, so what I'm gonna have you guys do now is I'm gonna split you guys into pairs. So we're gonna go into breakout rooms, and I'll paste this link. I'll paste this link in the November Slack chat. You can write some code that will basically do the same. We just counted down, but we're going to count up to a specific number. We're going to do that recursively. So it'll take 5 minutes. So let me stop sharing, pause there. So how was that?
Not too bad.
Chaotic.
Yeah, a little chaotic. Just trying that.
That
It's
was
hard to
horrible
find code.
trying to code with everybody else, putting new lines and pushing my code down.
Yeah.
I couldn't focus on anything.
Yeah. So this is an experiment. It's hard to find a good tool for this kind of thing. One that's free anyway.
Sure.
So I think maybe in the future what we can do is just people write code that, copy and paste the instructions or whatever starter code is given and work in their local environments and then maybe paste in after. But we can try out different things. So did anyone get it? Anyone feel like they got it?
Mm-hmm.
Okay. Greg, who did you work with?
I worked with Joe Patano.
Okay, let me share. Greg and Joe. Okay, cool. So you guys want count up, num, and count. So you print the count. So this is assuming that I feed in like 10, right? If I want to count up to 10.
Yeah.
Okay. So I'll print the count and it starts out at 1. Nope. People are still writing. Okay, so if num equals count, then you return. So what is if num equals count return?
So if so that doesn't return it. This is just to print it to the screen. So that basically just exits out of the loop.
Exactly, right? So it exits out of loop. So this is the base case, right?
Mm-hmm.
So if num equals count, then return. So this is the base case. This stops us from further recursion. Otherwise, we have our recursive case. And so our recursive case is num does not equal count, so anything else. And then we count up, so we get num. So num stays the same, right? But count gets incremented by 1. So this looks good. So the next time around, count, because it's now getting a value when you pass it in, assuming you called it without a value initially. So this will now be 2. So you would print 2 is 2 equal 10, let's say. No, so you keep going. So this looks like it would work for me. Did anyone else come up with a different solution? So we have, again, the basic structure is we have a base case, which takes us out of our recursive loop. And then we have a recursive case, which keeps going.
I got a question. How come on line 134, you were returning the function instead of just calling the function? Because in the previous count down example, we didn't return count down.
Yeah, so that's just, it depends on what your function is doing. So in this case, we're using our function for what's called its side effect. So we're just printing, we just want to print to the terminal. So you can execute this. It actually doesn't make any difference in this case. It's just going to return none in both cases. So we do
to do recursion, so that's wrong.
Count up. So we got to
Forgot
call
to
the
call it
function,
again.
of course. Thank you. Count up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And if we remove the return statement, you get the same thing, right? Because we don't really care about a return value here, but if we did, so there are cases when you're doing recursion where you do care about the return value. So you would need to return. All right, so I think that was, did anyone feel like they were just totally lost? And if you do, speak up, because I can't really see everyone at the same time.
At first, because just so much was going on the screen.
Yeah.
And then once it kind of slowed down and we figured it out, it was starting to get better.
Okay. So the way that we did this, it was confusing, but was the actual task, did you feel like it was just totally overwhelming? I had no idea what to do, or is it kind of, maybe this is a little confusing, but maybe given more time, you could be pretty sure that you would have come up with a solution. Maybe I needed more time. Okay. So that is fine. So I saw a lot of stuff. So, I'm not gonna closely look at all of them, but it looks like most people got the general idea. So that's good. And if you didn't, that's also fine. We'll talk more about this. And recursion, again, is something that you're not going to just get the first time you hear it. So people who understand it probably understood it before Platoon started. All right, so we've got this basic example. So we've looked at like this very like the simplest possible case of recursion, which is basically iteration, right? There are other more complicated problems where recursion really is like a nice fit solution. A lot of those problems are more complicated than what we want to talk about right now. But we'll look at a slightly more complicated example that we'll call divide candy. So here's the situation. It's Halloween or whatever. You've got you and your friend. Your friend has a bunch of M&Ms. And you want some of his M&Ms, but you just want to ask for them. So you come up with this little scheme. And so what you do is you say, you kindly offer to divide up your M&Ms, and you'll take all the M&Ms he has, right? Put them in one big pile, and then you'll divide that pile in half. Except you're going to use floor division, right? Because you don't want to have to cut up an M&M in the pieces. So if there's any remainder, you divide it in half. If there's any remainder, you get to eat the M&M, right? So we have a pile, we divide it in half. If there's any remainder, you get to eat it. And then you take that pile and then you start over again. You divide that pile, you divide it in half. If there's any remainder, you get to eat the M&M. And then you take the other half and you move on to the next. You create another pile. And you also divide that pile in half, and I think someone's mic's on. And you take that and you divide it in half, and then you eat an M&M if there's a remainder, and then you just keep going until something happens. So let's go ahead and write this out in steps. So we'll do one is, I'll use a text file instead.
Sounds like our function has OCD.
So we'll start with step one is, let's see, start with current pile. Step two is divide pile in half. We'll do, we'll call it floor division. And we'll check here. Okay, and then step three is let's do divide pile in half with floor division. And then, oops, this should be 4. If remainder eat candy. Step 5 should probably be predictable at this point, right? The other half of the pile is the current pile. So you start with the current pile, you divide it in half, you check if there's a remainder, you eat the M&M, and then half of that pile is your current pile. So we have a problem, which is I want to divide these M&Ms into a bunch of smaller groups, but this big problem is actually really just one small problem applied over and over and over and over again. So this is the kind of basic use case that you have for recursion. So it's called divide and conquer, where we have what seems like a huge problem. And if there's some way for us to break it down into one small problem you can apply over and over and over and over again, then you have basically a good fit for a recursive solution. So let's see if we can implement this. So I'll take this, paste it in here. All right, so I'm going to write a function. Divide candy, and we'll do pass. And we'll pass in like a number, like the number of pieces of candy they have. So we'll start with 10. So just, oh yeah, I actually had an illustration of this. Okay. Can people see this? All right. So here's our M&Ms, right? You have just a pile of M&Ms. So what we want to do is we'll divide it in half. So 1, 2, 3, 4, 5. So now we had 10, we have 5, so 5 and 5. Okay, that works. So now this is our current pile. We had 10 here, now we have our current pile. We divide this in half. So 1, 2, we have floor division, so that leaves us 2. So we get to eat one of the M&Ms, right? So we get to eat this blue M&M, that's for us. Then now this is our current pile again. We divide it in half. Okay, so half of that, half of 1 is 1, or half of 2 is 1, so that's even. We don't have to worry about that. Then we can, argue about whatever the base case should be. Maybe it's we try to divide this in half, and we get 0, so we get to eat this M&M. So we end up with a bunch of piles that are half as big, minus the thing. Okay, so this is the basic idea. So we'll try to implement that in code. Okay, so we'll pass in number of candies. So before we think about, getting the full solution to our actual problem, let's kind of take a step back and break it down into something simpler. So to a certain extent, what we're doing is we're counting down, right? We're starting with the number of candies we have, and eventually we're going to end up at 0. So we want to get a basic scaffolding going, we can start there. So we have a number, and then let's start counting down. So what should our base case be? So when we think about recursion, probably the first thing you want to do is figure out your base case.
So if number equals 0, then
okay,
that's the end of the function.
Okay, if number equals 0, then we'll return, for now, we'll just return nothing. Otherwise, we could do something like return divide candy and then num minus 1. So you do something like that. So this should give us the basic model, and we're not printing anything. So you run the right file. Okay, so we're not going to get any output, but we don't get an error. So let's assume that this works. Okay, so now we have a basic framework for thinking. We have a base case and we have a recursive case, and we're kind of decrementing. So now let's get it closer to what we want our actual solution to be. So we're not going to just subtract 1. What we're actually going to do is divide it, and we're going to use floor division, right? So we can go ahead and implement that. So if number equals 1, return, or number equals 0, return. Otherwise, then we'll do num equals num divided by 2. And we can just return num again. We'll go ahead and do an else statement.
And then we need to print num so we can see the number.
Yeah, we'll do that here as we're working. So we get 10, 5, 2, 1. So that matches what we saw here. We started 10, then 5, 2, 1. So that looks good so far. But we need some way where ultimately what we're trying to produce is a bunch of piles, right? So we can do this operation and eventually wind down to 0. Maybe we can do some print, you can, have a side effect where you're printing to the console. But what we actually want to do is return this product, which is our piles. So how can we, let's say that ultimately what we want to return is an array with, let's see, 5, 2, 1, 0, something like that, or 5, 2, 1. We could argue about the last detail, but something like this is what we want to return. So this is going to represent our piles. So 5 candy, pieces of candy, 2 pieces of candy, 1 piece of candy.
So could you create an empty list variable to start with, and then after the num floor division 2, add num to that list?
Okay. Does anyone else have any thoughts about that? Agree, disagree?
That should work.
Okay. So let's try that. So we'll do, we'll just call it piles, and that'll be an empty array. And then what we're going to do here is after we divide, we will do piles dot append num. And we need to pass this in as a parameter now. So piles. So now we're accumulating a result, right? We're not just printing stuff to the console. Every call is kind of a throwaway. We're actually accumulating a value. I'll need to print this out. So we're actually going to be, I need to return the value. So return piles. We'll get rid of our print statement for now. So hopefully we should see the result of our. So now we've created a pile of, a pile. And if we can use our debugger. We can check out the call stack here. So we'll step through. So now we have divide candy on the call stack, the first call. Number equals 10. We can hover over it and see that it's 10. Step over. So now I'm appending 5 to piles. Now piles, we can see, is an array with 5 in it. We'll keep going. We'll do another iteration, and we can look at the call stack. So this call stack will preserve the local variables here. So this is all the information. So when we talk about the call stack as being like a snapshot of what's happening inside the function, So we have this, it's basically an object. So this thing on the stack, this object has a local value and it has a value for piles. It has a local value of 2 and so on. So you can keep going, stepping through. So the stack is building up, and then I think this iteration, it should actually return. So now num is 0, it's going to return pile. So now all of these things, we'll watch the call stack, it'll just start popping things off the stack. So pop, it's popping them off. And then we get to the last thing, we're actually going to return piles, and there we go. Okay, so that is another slightly more complicated example of recursion, but oftentimes, so this is a way to preserve the value that you're returning from one call to another. So you do some stuff and you want to pass the result of that on to the next function call so that you will actually get something at the end. All right, so I'm gonna stop this.